Hello, everyone. My name is Chris Steinbeck. I'm a professor for Chem Informatics at the Friedrich-Schiller-University in Jena in Germany. My group is interested in natural products, structure elucidation, and natural product information in the broadest sense, and we are, amongst many other methods, also using deep learning for this purpose. Before we go into the center of the topic of today, which is informatics, datasets, and the curation of the future, in the context of using AI in chemistry, I would like to remind ourselves why we are so excited about AI at the moment, since there have been some fundamental breakthroughs and changes in the recent past. For me, the biggest game changer, so to say, in the last years was the event of Alphago. Alphago is a software by Google's DeepMind company to play Go against the best human players. And as they say here, our goal is to beat the best human players and not just mimic them. The first thing that caused attention was the game against Van Hui, the European champion in Go, which happened in London in October 2015. And AlphaGo beat Van Hui 5-0. So it was a very clear victory. Shortly after, and also after some technology improvements and changes, AlphaGo then played against one of the best players in the world, if not the best player in the world, Lee Sedol, in Seoul in March 2016. And also here, AlphaGo won, in this case 4-1. So Lee Sedol won one game, which in hindsight was a really great achievement, and people are still talking about this. And shortly after, the DeepMind team published the AlphaGo Zero, also followed by a number of articles, first in Nature and then in Science. And AlphaGo Zero was really a complete breakthrough in the field of AI, because for the first time, a deep neural network-based system was able to learn completely from scratch, without any human intervention, how to play Go, just using the basic knowledge of the Go rules. So where it can put the white and the black stones, and which moves are allowed and which are forbidden. And it did this by just playing against itself. Starting tabula rasa, just knowing the basic rules, and then over some tens of hours, through pure self-play, it surpassed superhuman playing strength. And then basically, while doing this, it rediscovered thousands of years of Go knowledge, and then eventually went beyond. An amazing achievement. So what does this teach us? The amazing success of AlphaGo was, first of all, made possible because AlphaGo had basically unlimited training data at its hand. And this recognition cannot be overstated. Of course, there were also hardware and algorithmic improvements happening, of course, before the whole event of AlphaGo, but there was certainly a decade of development into deep neural networks. But also during the first games that AlphaGo played against Van Hui and then against Lee Sedol, enormous progress happened, going from big farms of GPU hardware and complex sets of neural networks against Van Hui to eventually one TPU and a single deep neural network supported by a Monte Carlo search engine. But the topic of this talk here is data, and I think the recognition that AlphaGo Zero had basically virtually unlimited training data by playing against itself, just using the basic rules of Go, is a very important statement. And we will see whether we can learn anything from that for chemistry. Following the success of Alphago in game playing, Alphago Zero was eventually then also used to achieve the same in the games of chess and shogi. DeepMind continued to work in other areas, and they eventually decided to make a contribution to science by participating in the competitions for predicting protein structure from protein sequence. Many of you will know the CASP competitions, where the groups who develop methods for protein structure prediction compete against each other on a set of so far to them unknown sequences for which they have to predict the structures. The structures have been experimentally determined secretly, and eventually the group who does the best prediction wins. Alphago beat the best existing systems by a huge margin, and that caused a lot of attention in the scientific community. And there was also a very interesting analysis, a comparison of AlphaFold to AlphaGo, published by a gentleman called Bollinger in Academia Letters. And I'm citing here an important statement that Bollinger makes about AlphaFold 2. The last statement is a bit harsh, in particular because AlphaFold has clearly outperformed all existing systems so far. So there is something novel happening here, but there is a fundamental difference to the AlphaGo Zero case due to the lack of unlimited training data in this case. And basically in science, we will almost always, I'm showing a counterexample later, almost always deal with a situation where we have maybe big data, but still limited data at hand. So one thing that we have to ask ourselves in chemistry, do we actually have big enough data for deep learning in academic chemistry? I'm making this distinction here because data collection and data management in industry is a completely different league, so to say, compared to academic chemistry. Before we look into this, and I guess we all know the answer, I would like to make one important distinction. In order for data to be useful in data science and in deep learning, it must be open and it must be bulk downloadable. If you can download single data points from a website, that is not useful, and this should not be considered open data, even if you can freely access that single data point by querying. So what are the open big data in chemistry available? We have very large structure databases now. We have PubChem, we have Zinc with more than 100 million structures each, but those are mostly just structures. PubChem contains assay data, yes, but for example, important physical-chemical data such as spectra and other data are largely lacking. There are some open databases with physical, chemical, and bioactivity data, such as Campbell, for example, containing bioactivities against protein targets and other targets. But if you look at the numbers, you can easily calculate that for each target, there are a few hundred data points on average. There might be some well-researched targets, but a few hundred data points are just not enough for proper deep learning. We have databases like an NMR database that we created decades ago. There are some databases for pKa data of a few thousand molecules. But the bottom line is there are simply no databases with properties of compounds, which is what we are eventually interested in. We are not interested in structures, we are interested in their properties. There are not enough databases with properties to truly do deep learning in chemistry. Now, can we learn from other areas? Yes, just look at biology. This is the historical growth of omics data in the archives of the European Bioinformatics Institute, and there you see that in all areas, genomics, metabolomics, proteomics, microarrays, that is transcriptomics, and so on, we are on exponential growth curves. This is a logarithmic scale. We are in the petabyte area when it comes to genomic data. And areas close to chemistry, such as metabolomics, are also steeply rising. So why is that not working in chemistry? Certainly there is a cultural problem, and a problem how the area has evolved over time. But there must be now ways out of the data drought. And let's briefly, at the end of this talk, look into what we can do. First of all, actually, what we are talking about, AI, intelligent systems, deep learning, can actually even help us to extract data out of the publications that chemists have been publishing in the past. We can aim at developing systems for automatic curation, and I would like to give one small example how deep learning can help there at the end of this talk. But chemistry must also start proper research data management also in academia. We all know that that industry has this largely at hand. Some industry chemists might contradict now, but they have been using LIMS systems and electronic lab notebooks and structure registration systems for a long time, as we know. And in academia, this is completely rare. Now, things are changing. Many of you will have heard about the Fair Data movement and things like Go Fair and the Research Data Alliance. There are national and international efforts now to build research data infrastructure, even for chemistry. And it's very important that we make this change in culture in chemistry so that data sharing becomes the norm, and eventually we have the big data sets available with which we can do deep learning in the future. And then there will be game changers in many areas in chemistry once this is been made possible. In terms of building research data infrastructures, I would like to share one example with you, the NFDI for Chem, an effort to build a national research data infrastructure for chemistry in Germany. I have the honor to lead this. NFDI for Chem is not standing alone. It's part of 30 consortia in all areas of science, which the German government is funding overall with 90 million per year over 10 years. So this is a really big effort, a concerted effort amongst disciplines. And in NFDI for Chem, we have realized that one thing we need to do is change the way information is captured in academic laboratories. This is kind of a no-brainer, but if you look at the situation, here we have a lab notebook from 1927, here one from 2019, and apart from the whiter paper and the nicer handwriting, you will immediately see that not much has changed. There is a lot of implicit data in here, which is almost impossible to liberate. And if the poor PhD student who wrote this is eventually asked to deposit that data, he or she has to write it up again and submit it. And that's one of the big problems why people are not doing this. So one thing we said we would do in NFDI for Chem is change or try to change the thinking of people and the way we work in the academic laboratories by providing LIMS systems and ELN systems to the academic researchers. Those are open source systems which are now well established. And if we start to capture data in rich electronic forms from the devices using software tools and electronic lab notebooks as early as possible, then the deposition of open data in public repositories is just a click of a button and not days and weeks of typing things into painstakingly into submission systems of repositories. That change will need to happen in order to create big data sets in chemistry. I'm not going to talk about the social problems, the change in the minds of the people. This is another big effort for which we have at the moment for this within this talk here, no time for discussion. Another thing is going back to the past literature for information extraction using deep learning, and that brings us actually back to the starting point of this talk. When I heard about the AlphaGo 0 example and realized that the key is almost unlimited training data, we immediately realized that we had a similar application at hand, which is the extraction of machine-readable structures for the sake of putting it into databases from the printed literature. As you know, before 1990s, everything was printed on paper, and even those publications which we now find in the archives of publishers, they are before the 1990s, they are just scanned pages. They have been OCR'd so that you can read them, but the chemical structures, for example, they are just black and white pixels. And we realized that we could actually generate almost unlimited amounts of such images for training deep neural networks using image generation software, which we have now openly available. We could even make them as imperfect as the scanned images from the literature by adding noise, by blurring them, by slightly distorting them, and so on. So the images that the deep neural network would see would be very close to what we actually get when we scan journal pages. And it was in fact possible to train transformer networks so that with around 60 million images over the time span of days or even weeks in the end, to reach almost perfect translation capabilities from a bunch of black and white pixels, which to a human means a chemical image, back to a machine readable structures. And if you combine this with image segmentation networks and text mining methods for image extraction, then there is a hope that within a few years we can actually develop curation systems for getting that information out of the past literature again. So in summary, deep learning can be a true game changer if you have almost unlimited training data, or at least very large training data sets. Those data sets are virtually non-existent in chemistry, apart from exceptions like the one that I've just showed you. In order to change this situation, we need proper data management and proper data sharing to become the norm in chemistry, and we are far away from that, but things are changing. There are now initiatives with quite a bit of funding to change this situation. Also, deep learning can help us to rediscover data in the full text of our past papers. And apart from technological advancements, we are also seeing the necessary legal changes happening at the moment. Just a few years ago, if you would download a large bunch of papers from, let's say, any large publisher, they would just shut your university access off because you are not supposed to do this. But now we have legal changes that the right to read, if you own a license to that journal, you can also mass mine the full text, and that's an important condition for using deep learning to rediscover data in the full text of those papers. And with this, I'm at the end, and I thank you for your kind attention.